Welcome to today's special seminar on the topic of what can modeling information processing tell us about brains. I'm Lizier Yang from Beijing Normal University. I'm so glad to host today's seminar together with Ken Hongliang from Tsinghua University. Our guest speaker, Professor Lizier, will share his profound research outcomes on today's topic. First of all, I would like to have a brief introduction for the causal emergence community. Our causal emergence study group is being held by Storm Club, an organization of academic researchers and science enthusiasts exploring the fields of compliance systems and artificial intelligence established in 2003. The study group started in the summer of 2021 and has completed 4 seasons so far, covering topics such as causal emergence theory, partial information decomposition, causal representation learnings, and so on. Okay, and and the picture is our website, yes, for in English, yeah. So you can check this. And now, please allow me to introduce our guest, Professor Lizier. Professor Lizier is Associate Professor of the Compliance System Group of the School of Computer Science at the University of Sydney. His research fields include dynamics of information processing in complex systems and application of information theory to biological and bio-inspired networks. And he also created the CITT toolbox for compliance system dynamics. As for the topic, the local information dynamics is actually related to the series we have discussed before, such as computational mechanism and 5D. I found that Joseph's thesis is the fundamental framework for those works like such as 5D that uses information theories to describe and analyze complex systems. After that, I have introduced his framework and related applications on 3 articles on our Swarmer WeChat public account. Welcome to refer to these articles to have brief understandings on just thesis. But of course, you might go to what's the original thesis for the full understanding. Okay, and in today's talk, Joseph will talk about information dynamics, including information storage, transfer, and modification, and the application of information dynamics in computational neuroscience. You may have seen the abstract in the article on WeChat. Okay, now let's welcome Joseph.
Okay, well, thank you very much for the nice introduction, Mingxi, and thank you also to Kim Hill for organizing the seminar, co-organizing the seminar with you as well. It's a real honor to be here. This afternoon, 2 of the Chinese students in our complex systems group told me that they'd seen the seminar advertised and how impressed they were that I was speaking at it because it was a very well-known seminar series. So that's really nice to nice feedback for you guys and nice for me to know about that as well. 2 things I should probably mention before I get started. Number 1, as I said offline at the start, I've had a bit of a cold during the week. So if I end up coughing a little bit, I apologize for that in advance. The second thing, I'm happy to take questions during the talk. I'm not sure what your usual process with that is. If you prefer people to hold it to the end, we can do that. If you're happy for them to ask questions midway through, I'm happy to take questions. So it's up to you guys. If you would like us to do questions midway, then please let me know when someone's got a hand up or something in the chat, and we can have a pause and handle that.
Sure, okay.
Okay. Topic of my talk tonight is what can modeling information processing tell us about brains? So as I'm sure you've guessed, my research area is about information processing with particular application to neuroscience. So let's start to unpack that a little bit. It would be tautology to say that brains process information. We talk a lot about how brains take in inputs from the sensory information inputs from the sensory regions, how they process those inputs, combine them, for example, combining auditory information and visual information to process those inputs and combine them into new forms of information and to make cognitive decisions about them. We talk about how the brain outputs information via the motor system, for example. So we talk a lot about information in brains and the processing of information in brains. To put this in a bit of a wider context about my research, I'm not a neuroscientist, I'm a complex systems scientist. I mean, I guess really at the end of the day, I'm a computer scientist, but my specialty is in complex systems rather than specifically in the brain or neuroscience. So I'm thinking a lot about complex systems in general and information processing in complex systems in general. So complex systems, as I'm sure everyone in the audience knows, are large systems of many interacting individual entities where the system behavior is some kind of non-trivial result of the many interactions between those entities. Complex systems exhibit self-organization, emergence, and collective behavior. And we use tools from complex networks or graph theory, information theory, game theory, agent-based modeling, dynamical systems, and so on to study them. There are applications of complex system science in many areas because complex systems are all around us. I'll go through some of my favorite complex systems in some of the next few pictures. Firstly, thinking about collective animal behavior, schooling or flocking or swarming. This picture here is showing a school of fish. What we're seeing is how when some predators might come in from one side of the fish, what's going to happen is that the fish that are closer to those predators will turn away from them. Even just a little bit of a turn is enough for the next fish along on the inside of the school now to react to that turn from the ones on the outside and to turn a little bit themselves. Then the next fish again on the inside of the swarm or school after that, the next ones again will turn a little bit also in reaction until what you get happening is this cascading wave of turning passing across the school. So that initial movement triggers this cascading wave of information about the incoming predators across the school. Those kinds of cascading waves of information we see in many different complex systems around us. And it's known as the Trafalgar effect because the British used it for signaling in the Battle of Trafalgar many years ago, because here the information travels much faster than any individual in the system could travel on its own. Fireflies are another one of my favorite complex systems. Here, fireflies simply flash on and off. And what they do is they're observing the other fireflies around them. And they're speeding up or slowing down their flashing in response to what the others are doing. Just like we speed up or slow down our own clapping in an audience in response to the claps that we can hear around us. If we feel like we're clapping a little bit behind everyone else, we speed up. If we're clapping a little ahead of everyone else, we slow down. If all of the people in the audience or all of the fireflies in the group are doing the same thing, the group will eventually synchronize. And so what we end up seeing is that the group of fireflies tends to synchronize their flashing. And we can talk about how the fireflies are kind of communicating via their flashes. They're intrinsically communicating to each other via those flashes because those flashes from a source firefly will cause a target firefly to either slow down or speed up its flashing. So there's an intrinsic communication there. And there's decision making as well. The fireflies will be reacting to each other, taking on board that information that's come in from the flashes, combining it with its own stored information in its phase and updating what it's going to do about its phase and storing the information back to its phase again when it updates it. Ant colonies are another interesting complex system. We talk a lot about how ant colonies compute the most efficient routes from food to the nest, and they store information about those routes in pheromone trails in the environment. Cellular automata, as you know, the background to my work, you know that these are possibly my favorite complex system overall. Cellular automata are a canonical complex system where there's been a lot of discussion about computation in this kind of complex system in terms of how gliders transfer information and blinkers store information, for example. So in all of these systems, the way I've been speaking about them was very deliberately using the language of communication, as I'm sure you picked up. In all of them, I was talking about what the system overall was computing, how information was transferred, how it was stored, and how it was processed. So given that we often use this language of computation, at least qualitatively, to talk about complex systems, my research focus has been about how to model information processing in complex systems and how to do that quantitatively. So the word model there, what we mean is, how can we quantitatively model information processing in a common way across all these complex systems in a way that can bring useful insights about the dynamics of all of them. So with information processing or computation being our focus, the natural point to start is going to be to ask about how computation is approached in computer science. Now, in computer science, the primary theoretical or abstract model that's used when we talk about computation is a Turing machine. So in brief, what a Turing machine is it's a deterministic state machine operating on an infinite tape. And what it does is it undergoes a repetitive instruction cycle. The Turing machine has a reading head positioned over one point in the tape. And the first part of the instruction cycle is to read what it can see on that part of the tape. Then, based on its internal program and its internal state and what it read on the tape, it might write something back to the tape. And then again, as a function of those three things, move the head to somewhere else along the state. Then again, as a function of the state, what it read and what its program says, it might update its internal state, and then it may move to the next instruction, or it may halt altogether. So this is how computer scientists tend to talk about computation in terms of modeling computation in Turing machines. They're very powerful theoretical ideas to capture what computation is and what can be done with it. But the question is, does this actually help us to understand biological computation in the world around us? And I'd say not really. I mean, we can use Turing machines to study computation in complex systems around us. We can produce a program that simulates all those complex systems I just showed on the previous slide. Taking a flock, for example, we can implement a model of a flock in NetLogo or any other computational language. And we have a computational model then that shows us what that complex system is doing. Is that really helpful, though, to understand the computation in those systems? And I'd say probably not really. Fundamentally, yes, we can look at the lines of code and we can look at exactly what's happening and what a Turing machine would do, but it's not really helpful to understand the dynamics of those systems. It's helpful in terms of running simulations and understanding what's happening there, but not really in terms of unpacking the computation in those systems themselves. So what could we take away from computer science views on computation that might be useful in terms of understanding complex systems? And I think what's really good about computer science views of computation that is still very valuable in complex systems is that when we're thinking about computation in terms of Turing machines, we're thinking about computations that have very well-defined inputs, which here was the data that was written on the tape at the beginning, very well-defined outputs, which is what's written on the tape at the end, a very well-defined algorithm being the program written into the Turing machine. And then additionally to that, when we're thinking about computation from a computer science point of view, we're often thinking about what the task is and what the terminating conditions are. Those aspects are not necessarily as useful, but I think the first three, inputs, outputs, and algorithms to map from one to the other, are really was a useful part of how computer scientists study computation that we can still take with us. The algorithm is really the most important part. How is it that the inputs are translated to the outputs? How can we unroll that to understand what algorithms are being implemented in computation in complex systems? And so to do that, there's a really nice quote from Melanie Mitchell where she says, if we want to understand computation in complex systems, especially in terms of those algorithms, then the language of dynamical systems itself may be more useful than the language of computation. And that's obviously where I've started to suggest we should probably head. So let's have a closer look at what that may mean. So another way of putting this was that the term intrinsic information processing from Feldman and Company in 2008. It's a very inclusive view of computation that says intrinsic information processing occurs whenever a system undergoes a dynamical process that changes its input state and outputs into some later state and outputs. And this maps extremely well to what I was just saying about computation, some of the useful features of it that we may take from computer science and using complex systems, thinking about simply the way an algorithm turns a set of inputs into a set of outputs. This is basically restating that with a dynamical systems view on it. To look at that in a bit more detail, what does this mean? We can think about it in terms of the human brain as an example. So we can think about how the brain may start in an initial state, where the colors here on the different parts of the brain represent different activity levels in different areas as the initial condition. We then take some inputs, for example, some sensory information, and the brain undergoes a dynamical process. Those different parts of the brain interact with each other and may be taking on extra input through time while they are interacting. And then at some point later, we've got a final state represented by a different pattern of activity across the brain and some outputs, some motor information, for example, exiting the brain. And again, the outputs may have been happening all the way along the dynamical process rather than just at the end. And so this is kind of the view that Feldman and company are advocating regarding thinking about complex systems as intrinsic information processing entities, that they are constantly changing inputs and initial conditions to final states and outputs via dynamical processes. And we can think about that as a form of computation. So this view is retaining the focus on inputs and outputs and algorithms, but not really shoehorning a view of computation in the complex system into the Turing machine. Instead, this is thinking about distributed dynamical processes as the algorithms that change those inputs into outputs in the system. So this is a very inclusive view of what computation is. It's a very inclusive view. It's almost saying that any system around us is computing in some sense. So because it's so inclusive, we still want to be more precise. We don't want to just leave it there. We want to say, okay, well, how can we make these notions more precise so they're actually useful? Well, okay, let's start to think about how the information is processed, because as I say, we've now said all these systems, the same ones that we were just talking about before, we can view them as information processing entities. So how can we see information being processed in them? So what we have to do is to acknowledge that, okay, we've talked about mapping inputs to outputs via some algorithm. But we have to acknowledge that the information processing isn't just a mapping from inputs to outputs at the system level as a whole, but it's actually happening inside the system, in the distributed and collective interactions inside the system. So at all the points in the brain, they're all interacting through time during that transition. That's where the information processing is happening. It's not just a one-step jump from an initial state with inputs to a final state and outputs there. So acknowledging that, how can we start to make these notions a bit more precise? And so a starting point is to realize that when we're talking about computation or biological computation in these systems, we were talking about it in terms of memory and signaling and processing. For example, when I was giving those descriptions earlier, I talked about memory in the Firefly system, for example. I talked about how information was stored in the phases of the individual fireflies. They stored their own phase and then adjusted, used that information storage with information that was coming in order to update their phase, and then stored it individually again. So there were information processing events happening at every firefly across the system at every point in time. Similarly, we talked about signaling a lot when we talked about the fish example. We talked about the fish, the turning waves of information that signaled about the incoming predators. So we talked about signaling, we talked about information flow across the school from one fish to another as a distributed process across the fish. So we're using these terms a lot qualitatively. And so to make these notions more precise, what we can do is to move on to make them quantitative, to make our quantitative model about information processing in the complex system, about quantifying each of these operations on information, to quantify how information is stored, how it's transferred, and how it's modified in the interactions at every individual in the system at every point in time. And if we can do that, then we're really starting to get at exactly where the intrinsic information processing is happening. and to be able to quantify what is happening when and where across the system as a whole at every point in time. So the goal here is that we're trying to model intrinsic computation in the language it's normally described in. So these terms on the left represent a representation of the kind of quantitative language that's often used to describe computation in complex systems. So we're trying to take that qualitative language and make it quantitative with these terms here. And the goal is that by doing that, by mapping our quantitative terms to the qualitative terms that are often used to describe computation in complex systems, then we should be better able to understand information processing in these systems around us. For example, information processing in the brain. We should be better able to understand it that way and its deficiencies, for example. In other words, if we can model information processing in ways that can provide answers to meaningful questions that are phrased like this, then we can help our understanding of information processing in the brain and other complex systems. So that's kind of the background to the motivation of why we want to study information dynamics, the dynamics of information processing in complex systems. From this point forward in the talk, there's sort of three parts to what I'll speak about. So I'll speak a little bit about, okay, well, what is information? How are we going to measure information? And in particular then, how do we model information processing using this philosophical approach that I've just sort of talked through. And then finally, the last part of the talk will be giving some examples of what approaches aligned with this view can reveal about the brain. So let's move to the first part about what is information. Now, I know this reading group has looked at a lot of information theoretic approaches to complex systems, so I'm not going to go right back to the beginning of what information is, but I'll just very briefly point out a couple of things that I use when I'm introducing information theory to students, because I think they're useful concepts to have in mind. So obviously we're turning to information theory when we want to quantify these operations on information. And when I'm introducing what information theory is to my students, I often use Guess Who as a starting point. Guess Who is a really nice game to introduce what information is. Now, I actually don't know whether you guys have Guess Who in China, so I'll describe very briefly what the game involves. You can see you've got two people at these game boards here. These are oversized game boards. They're really, in real life, there's something that can sit on your lap. This is from a exhibition or something. And what you've got is, say you're the red player here, then you've got 24 cards here that are turned up, and these are the potential identity of the card who your opponent is holding. So you're trying to guess who the opponent is. And at the same time, they're trying to guess your identity out of the same 24. So you've got your identity here. The way you do it is you take turns asking yes or no questions. So you can ask a question like, is your person male? You could ask a question, is your person wearing a hat? Or does your person have brown hair? Does your person have blue eyes? And they have to answer truthfully, yes or no to that question. And based on the answer, you can then eliminate certain characters on the board in front of you. So if you ask the question, is your character wearing a hat? And they said yes, then you know that you should flip down all the cards here of people who are not wearing hats and only leave up the ones wearing hats as the remaining possibilities of who that person could be. So each answer allows you to eliminate certain possibilities. It reduces your uncertainty about the identity of the other person's character. And so you go back and forward asking questions like this, and gradually you whittle down the possibilities of who the other person could be until you get down to having only a single player, a single identity remaining, and then you've eliminated all the uncertainty and you know exactly who the opponent's character is. You have full information about that character. So as I'm sure you can imagine, this is a really nice game to play and thinking about what information is and how information is conveyed. So I use this with my students a lot. And if you're interested in the lectures about that, all my information theory lectures are available on YouTube, actually, so you can see how that's used, in fact. So in terms of defining what information is, I guess it's not really going to be surprising that my view is that information is all about questions and answers. So just like we saw in Guess Who there, you're asking a question and you're receiving an answer. So this concept of questions and answers comes up a lot in information theory. So information itself is the amount by which one variable, be that an answer, a signal, or a measurement, reduces our uncertainty or surprises us about another variable. So here we ask a question about the identity of the character, and we receive some information. And that information reduces our uncertainty about the character, or to some extent surprises us about what that character, who that character is. So of course, we need to quantify both what uncertainty is, which is entropy, and uncertainty reduction, which is information. And again, as I say, I know you guys know what these quantities are. I just thought it might be nice to spend a couple of minutes going through some of my perspectives on some of the fundamentals there. Let's flip past that. What I like to do next in this talk is to talk about some of the things that we can measure with information theory. And again, I know you guys have seen this a lot, but for the purposes of just building the story, I'll keep going with it. So in Guess Who, we can measure all sorts of things. We can measure how surprising it is to receive a particular answer. How surprising is it that the sex of the character was female? We can ask how much uncertainty there is about the identity, for example. We can ask about what is the uncertainty reduction about identity from hair color. If I find out what the hair color is, how much is my uncertainty reduced about the identity. I can ask specifically how much information do I get about the identity if I find out that the hair color is red, for example. I can ask more specifically, again, how much information do I get about the sex being female from the hair color being red, or in the context of knowing the person's wearing a hat, how much information did I get about the sex being female from the hair being red? And here you can see the direct mapping between these questions and information content. For example, in the first one, this is something we'd measure with Shannon information content. We would use Shannon entropy to answer the second one. We would use mutual information for the third. The fourth is a specific information, so a partially pointwise mutual information there, whereas we now go to a fully pointwise or local mutual information in this answer here, and then finally a fully local or pointwise conditional mutual information in the last one. So those questions that were phrased very naturally about the game are answered really easily with information theory. And we can, of course, ask the analogous questions in neuroscience. So we can take a classic experiment where we have neural recordings at different points in the brain, where we've asked someone to make a face house discrimination. So we've shown them a picture. We've asked them, is this a house or is this a face? And we're measuring what's going on in the brain while we're seeing how they're reacting to that stimulus. And so all of the questions I've just listed out about Guess Who, we can ask all those same questions in this neural experiment here. We can ask how surprising it is that the object is a face. We can ask how much uncertainty there is about the object, whether it's a face or a house. We can ask about uncertainty reduction about the object from a specific brain area, if we look at the neural recordings there. And we can ask about the uncertainty reduction that we get if I tell you the specific value of the recording in that brain area. And all those questions are questions about the nature of neural codes, for example. Moving on to the last two questions, we can ask about the pointwise mutual information between two specific values of the neural recordings in those brain areas. And we can ask about the conditional value as well, given the value in another brain area. And now we're kind of moving on to more functional relationships between areas in the brain. So, of course, information theory is super useful for neural data analysis because it allows us to answer these kinds of questions that are very naturally phrased, and it allows us to do that in a model-free way that captures nonlinearities, and we have estimators for different data types and multivariates. So this is a really key advantage for mutual information. We can ask multivariate questions about how multiple brain areas are related to the stimulus or to each other, and so on. And those sorts of questions are much harder with other kinds of approaches. So the kinds of questions that we saw, as I say, are both about the nature of neural codes and functional relationships. But what's of kind of more interest for me is about modeling information processing dynamics. So it's thinking about the dynamic interactions between those brain areas rather than static relationships between them or between them and the stimuli, for example. In order to get at these questions, we really need to come back to our views on information processing that we started a little bit earlier. So returning to this question, how can we model neural information processing dynamics? Well, returning to the idea that we had about how we've got an intrinsic information processing taking place in the dynamics, changing this initial condition and inputs to a final state plus outputs. Well, the first thing we could do, taking our views on computation before, is that, well, we could build a computational model at the system level. So we could sort of build this automata that represents the system as a whole, and it's taking some inputs from the environment and has an internal state and has some kind of algorithm or mapping that takes those inputs in initial state and maps out a next state or output from them there. We could do that at the system level as a whole. But we know, as we said before, that the information processing is happening in the distributed dynamics across the system in all points in the system at all points in time as we go from this initial state to the final state. So that's not really what we want to do. We don't just want to stop there at the system level. So where are the interactions? Well, as we said, they're between the coupled elements of the system. So we've got some elements of the system that are coupled here in some complex network. Now, when we're talking about the brain, these could be individual neurons that we're thinking about in our little model now of what's going on inside the complex system. These could be individual neurons that are all coupled to each other. Or maybe we have a neural model that's at a higher level. We might be talking about a brain regional level model, something on the scale of neural mass modeling, for example, where our nodes in our model of the brain are brain regions rather than individual neurons. And that's going to be a bit more of a tractable model. Whatever the nodes in the system are that we're thinking about creating our model, at the level at which we're creating our model, they're coupled elements of the system. And they're also generating time series activity. Each one of the nodes in our system have time series activity. Now, this could be in a neuroscientific setting. This could be fMRI activity if our nodes here are brain regions of interest in the system. They could be beamform sources if we're looking at MEG data. So our nodes could be beamform sources, and we could have the activity at each of those beamform sources through time that we're looking at as well. In a very different kind of system, these could be our nodes in the system might be equities in a financial market, and we might be looking at their price dynamics through time. Whatever the kind of system is, the point I want to make is that we've got individual entities in the system that we're now going to look down at that level rather than just thinking about the system level. We're going to look down at those individual entities, and we're going to look at their own time series of activity. And we know that the interactions are happening between those individual entities at every point in time. Okay, so we've got this multivariate time series between the nodes in our complex network that we're modeling the system with. So how can we model the information processing dynamics between these nodes, these entities in the system? Well, what we do is we recognize that there's actually many parallel local computations happening with the system. We don't just have one single computation happening at the system level. We've got computations happening at every node in the system at every point in time. So here now I'm drawing one little automata to represent what's going on at every node at every point in time. So right here, for example, if we think about focusing on node X for a moment, node X is an automata that we're going to use to model the computation on node X. Node X will have an internal state. Node X will take inputs from other nodes in the system. For example, here we can see it's taking inputs from Y1 and Y2, which represent the arrows incoming into node X. And then at each point in time, node X will process what's going on and produce a new output and update its internal state there. And that's just one local computation inside the system. We've got many parallel computations happening at every entity in the system at that same time point. So this is happening all over the system. We're now starting to think about these local time updates at every point in the system as local computations. And each of them has these features that we identified before from Turing machines that are super useful. They each have inputs, they each have outputs. Those inputs and outputs are now going to be coupled across multiple time steps. And they each halt. Each computation runs for one time step in our system and then halts, and then runs again and halts, and so on. So we have these many parallel local computations, and this is how we can now start to think about modeling the neural information processing dynamics. This is giving us a framework with which to approach it. And what we can do specifically is to approach these computations by measuring the information storage and transferring them. They're not necessarily so useful on their own. It doesn't really necessarily matter exactly what's happening in each of these computations. What's happening is that we can study them using these operations on information that we already identified were the way that people spoke about computation in complex systems, using this language of information flows and information storage, which is that sort of language that computation was being spoken about. So now we've got a framework that we can actually look at measuring those at the appropriate points in the system that will now align with how people are talking about the computation in complex systems. And so if we do that, that's aligning with the philosophy that we were talking about before. And so if we can measure these entities, then we'll be able to establish an information theoretic footprint of what's going on in the dynamics in the system. So let's have a look at exactly how we do that. The first measure that we use is called active information storage. So this is thinking about modeling, and this is thinking about the first stage of modeling information processing, which is to ask in the update. So we talked about how we're thinking about the update in just one part of the system at a time, just about node X, for example. So we're going to break down what's going on in the computation for X in terms of how information is stored and transferred. So breaking it down, firstly, in terms of information storage is just the first step here. So when we ask about the information storage in node X as it updates to work out what its state is going to be at time n+1, given what happened earlier in the system, information storage characterizes how much information about the next observation, the one that is being computed now, how much information about that can be found in the past state of X. Now, the past state here means the past k embedded values of time series X. So when we talk about the past k embedded values, this is another link to dynamical systems. This is thinking about a Tarkin's embedding vector to capture the underlying state of X. We can ask how much is that underlying state contributing to the time series update of X in information terms. So to do that, we're just using a mutual information, measuring the mutual information from that past, embedding the past k steps of X, how much mutual information does that hold about the very next value of X. So that's attributing any information that we can see in that past vector as being information storage in our model. That's going to capture anything that's internally stored in X, mechanically stored in X. It's also going to capture information that is stored in a distributed fashion by X in the system. Maybe some information that went out from X into other nodes in the system and then came back later. All of that is going to be modeled out. So the excess information, the excess entropy or predictive information will capture the mutual information between that past embedded state, but also a future embedded state. So for example, we might have some information from 3 steps back in X that is then used again, maybe 3 steps out in the future of X. Now that's something that I do see as an information storage, but it's not information storage that's being used right now. It's kind of being held somewhere in the system for later. Whereas with the active information storage, it's a subset of that total information storage that the excess entropy or predictive information captures. It's the subset of that that's being used right now in the computation of X at time step n+1. Does that make sense?
Yeah, it makes sense. But another question is, you mentioned that some of the information is stored somewhere in the system. So
yeah,
what is the somewhere there?
Yeah, great question. Great question. let me flick along 2 slides to an example without going through all the details of the example yet. The example is my favorite complex system being cellular automata. So here in the cellular automata, what we've got is we've got a one-dimensional array of cells here, which are all updating synchronously in discrete time, and they're all using the same rule to update themselves. So each of these, this is an elementary cellular automata where each cell only updates itself as a function of itself and one neighbor either side. So it's a very, very simple system. Yet, despite its simplicity, we can get really interesting complex patterns here. So this is rule 54, which is known as one of the complex CAs. And what we can get with these really interesting patterns is if we have a look at just one cell here. So if we pick this one here that's black, then black, white, then white, black, white, black, white, and so on, you get these really interesting background patterns that are repetitive, both in time and in space. Now, let's pick a short sample here. So if you can see my mouse, if I'm tracking through what's going on from this cell here, where we've got two white, then 2 black, then 2 white. Actually, the pattern's just broken there. Unfortunately, I'm looking for a longer one that doesn't break because we've got some gliders going across that are breaking the background pattern. But that background pattern that I was looking at where we've got, this is a nice longer one where we've got 2 white, 2 black, 2 white, 2 black, 2 white, 2 black, and so on. That pattern can repeat for a while. So that's a period 4 pattern. A repetitive pattern like that is something that we would characterize as information storage dynamics. We only need to look at the past of that entity to be able to predict its future. We don't need to see to look at information that's coming in from anywhere else. We can perfectly predict that repetitive pattern. Yet, that repetitive pattern can't be supported by, mechanically, can't be supported by only that cell's internal state. It must mechanistically be supported by the interaction between multiple cells. If it was a pattern that was only supported mechanistically by that one cell alone, the only repetitive pattern you can have is an alternating pattern, 0, 1, 0, 1, 0, 1, 0, 1. You can't do anything more than that. To get this longer pattern, 2 black, 2 white, 2 black, 2 white, that has a period longer than 2, you mechanistically need to have interactions taking place. So mechanistically, the information must be being sort of offloaded into the environment and then coming back later, mechanistically. But with our information processing view, we will model it as information storage. So that's the distinction that I want to make, that mechanistically, to support a longer pattern like that, the information must be causally being stored elsewhere. But in terms of our view of splitting what we would characterize as information storage and what we would characterize as transfer, we will characterize that as storage. Does that make sense?
Yeah, makes sense. Yeah, someone has raised hand. Maybe you could open your mic and ask.
Okay, yeah, I have another question which is related to this one about the information storage mechanisms. So you're saying that to predict or to get the next information in the next time period, you have prior information from the node, right? The state information from X. So, but when we are in terms of information processing itself, there are both explicit information, but also there are the system dynamic itself, which basically, if you think about the like the example you're making in a cellular automata, the rule itself also carries information, right? So the information dynamics, or like in the physics world, the physical laws about how these individual element of the information react to other type of information itself, the rule also carry information, right? So for example, if we talk about physics, we're talking about like the cellular automata rules, like rule 54. These, those informations are also very important in terms of like the predicting the future, right? So if you know what is the underlying rule, like Newton's law or the general relativity and so on, we then have that information from the physical law itself. It's going to be carried into this complex system itself. And how do you represent and also account for the information that are kind of like one level below the explicit information in the state, but also the interactions between the state and informations?
Yeah. So I would think about that as being that information is kind of baked into the probability distribution functions that we see in the dynamics of the system here. So the cellular automata rule number, for example, controls all the different combinations that we can see of past configurations and their probabilities and their combination with future values and the joint probability between those. So Rule 54, for example, will generate different probability distribution functions across those that then get entered into the mutual information calculation. Then, for example, Rule 110 or Rule 18, they will generate very different probability functions here, which would then go in to the mutual information calculation in a different way. So that's where I see those the underlying physics of the systems coming in. They're basically controlling the probability distribution functions that you will measure. So they're there and they're controlling what you're getting in some sense. That's one way to look at it. Another way to look at it might be that's kind of looking at it as a single possibility world that we can only have the one rule. That's not necessarily the case, though. Say in the brain, for example, we might have the brain acting in different modes. So we might have, some kind of high energy mode where we've got a large release of one specific neurotransmitter that puts us in a more attentive mood, for example. We might have very different activity if we're in a low attentive mood, if there's low release of that neurotransmitter. So they're kind of the underlying physics of the system might be changing. There might be different world possibilities. And so there, you could account for that in many different ways. So you could have that, let's say it's a neurotransmitter that's controlling your physics of the system. So it could be a variable itself in the system that you consider as an input to the system. You could look at it like that. You could alternatively, you could look at it as a conditional variable. So we could ask all these questions about information in the context of what the specific neurotransmitter level was. So we can make these all conditional information calculations conditioned on that value. Or we might average across them. We might average across what the ensemble is that we might experience of that particular neurotransmitter. We could look at it that way too. There's no one right answer. Like everything with information theory, it depends on what question you want to ask of the system, how you would handle it. Does that answer your question?
Yeah, thank you. It answers part of my question, but I think the underlying question is really about like intelligence, right? For example, if we're thinking about human intelligence in the brain, we use informations not only from the state, from the perceptual part of the brain, but also we make a lot of deductions and we use our own kind of like rules or heuristics and so on to compute the future. Like in the ChatGPT, it's used the whole information is learned about the past and from prior interactions and to predict the probability or the next state information. And I think the brain also have that kind of like mechanisms in terms of like you use the rules that are stored and then you understanding of the rules, of the physical laws and so forth to compute the future, and then to get information output that is not only from the system dynamic, but also from a kind of like a higher level intelligence, right? So I'm just trying to see how that intelligence or the memory about those system dynamic itself got reflected in this process there. So.
It's a difficult question. So there could be many ways that could come in and influence what's going on here. So the past experiences of the brain or any complex system can shape the underlying network structure on which those dynamics are being generated on. So, you know, later dynamics will reflect how the system has been changed in some way. Synaptic connections have been formed and broken and so on. So you've got pathways that have formed that were different from what before and changes the dynamics that are capable of those, and that in turn changes. Like I said before, the CA rule kind of bakes in what your probability distribution function is across the dynamics that you're seeing. And here in the same way, the past experience of the network will change its shape, which will bake in different ways the kinds of dynamics that are possible to be seen here and the distributions of those that you're seeing. I guess that's how I see what you're asking, but again, maybe I'm not quite understanding.
Thank you very much. I think it answers my question.
Yeah. Okay. Good. Okay. So yeah, we're just talking about active information storage, and it talks about why it was called active and so on. But in the end, it's a mutual information between that Tucken's embedding of what the past state is and the very next value. Now, one thing that I like to think about is not just an average mutual information here, but a time resolved or pointwise or local value for that, which we can write in this different way. So up the top here, I haven't written out the full mathematics for what the mutual information is. As you said, I know you guys have seen the mutual information a lot, so you probably don't need to have a look at that. But it is effectively an expectation value over what we're seeing down the bottom here. So here what we've got is the information from a specific past state. So from one specific realization, here we're using the lowercase x to indicate a specific realization of the uppercase variable. So the information from a specific past state about a specific future state here. So that pointwise value we'll write as a log ratio like this. So this is telling us the information from a specific past state about the specific future state that we're seeing there. So it's a pointwise or local or time resolved value, which means we have one measurement of this local active information storage at every point in space and time across the system. So here, just thinking about one point in space, x, we've got one value of this at every time step. So we can use this and we can plot it and represent, for example, the dynamics of information storage across time for this variable. And we can look at how it changes through time and how that relates to the dynamics of the system, for example, which we'll see in that cellular automata example in a few minutes' time. These kinds of local mutual information values, you might have seen them recently pop up as edge time series from some of the neuroscience groups in Indiana. That means just a local or a pointwise mutual information value. Let's have a look at our second measure for information dynamics before we have a look at an example. So the second measure that we tend to use is now stepping beyond that, going beyond that first step of characterizing information storage, and then asking as a second step in our understanding what's going on in the processing at node X, how much information is contributed to the information processing from some source node Y. So here we use the transfer entropy for that. And the transfer entropy asks how much information about the next observation of our target process can be found in the previous observation of our source process Y in the context of the past state. So this one here is just a conditional mutual information. It's a conditional mutual information from our source value to our target value in the context of the past. So I'm saying very strongly here in the context, that means just conditional. We're conditioning on that value in our conditional mutual information. So the transfer entropy here is an average information from the source that helps us predict the next value in the context of the past, or helps us to predict the state transition in X. So this is a Granger-like measure, Granger causality-like measure. They are in fact exactly equal if we've got a linear estimator on continuous value data for the transfer entropy. Importantly, it's a dynamic measure of information flow. It's not static. The conditioning does a few very special things. So one very special thing that conditioning does is it changes this into being about the dynamics of X. It's changing it into being about what Y tells us about the state update in X. That's one particular thing. The second particular thing is it's helping us complete our modeling. What it's doing is adding in only complementary information. What we're doing here is we're breaking down or regressing the total information in our next value of X. We're performing an information regression on that when we're looking at the information processing here. Our first step was to look at the active information storage in X to account for the past of X. Then as a second step, we've taken the transfer entropy here, for example, from the Y1 about X. And by conditioning on the past of X, what that's specifically doing is it's separating anything we're calling information flow here. It's separating it from what we call information storage before. So that conditioning has a very important role to properly separate information storage from transfer. So that's really quite important. We can continue that information regression and look at higher order terms like the conditional transfer entropy. And there are other ways to break down those higher order terms as well, which we won't really go into today. The transfer entropy, it's not causal. This is another important thing. Just like before when I talked about information storage, capturing what might be mechanistically stored for X in other variables, here the transfer entropy is not necessarily about the causality or the causal effect of Y on X. These are two different concepts. This is attributing information flow in our model to Y. It's not about the causal effect of Y and X, and we've written about that at length in some other articles, which I haven't actually referenced here. But if you've seen, I know you've talked about seeing the thesis, so you know the sections I've written about that there. Similarly, like we talked about with the active information storage, we can measure local transfer entropy here. So we can measure not just the average information flow, but from Y to X, but we can measure the information from a specific source value, from this specific source value to this specific target value in the context of exactly what we saw in the target past. So that allows us to attribute point-wise information that's flowing that we would model as flowing right now at these values here. And of course, our transfer entropy is the average across all of these values that we have in our sample set. So we can do this at every point in space and time in the system. We can write down these information flow values. Let's have a look at the example. So I've sort of briefly introduced this about looking at cellular automata as one of my favorite complex systems and how we've got interactions, very simple interactions, just interactions with one cell on either side only here. And the first thing we can do is we can, well, I'm showing you them all at once, but let's look at this first one here. We can look at the information storage at each point in space and time in the system. So at each point in space and time, say this point here, we look at the raw values, the raw value of that point. We look at the raw value of the past k points leading up to it, and we can ask how much information those past k points gave about the next point, and then plot it on here. And what we see in our profile of information storage at every point in space and time in the CA is that the blinkers, the static structures here, so they change through time, but they don't move spatially. So it's blinker structures, and the background repeating patterns, background domains, they're the dominant information transfer entities. The information transfer is high, shown in the sort of aqua blue here, in the static blinker entities and in the background domain entities, whereas it's very low, or in fact it's negative at the gliders. So we can't really see the gliders too well here. If you sort of look for any discontinuities in the pattern, if you sort of trace a vertical row down until the pattern breaks, so we've got one breaking here where we were doing 2 black, 2 white, 2 black, 2 white, and then suddenly we were on a black, white alternating. So when that pattern changed, that was when we encountered a moving glider structure here. And what happens is when that pattern changes, we get a negative information storage value, which is something we call misinformation. What's going on there is that our background pattern became misinformative about what was happening in the future. So let me just go back 2 slides here. Oops. So looking at our local active information storage, it can be negative when this posterior probability here of the next value given the past is actually lower than the probability of the next value alone. What that means is if we looked at what the past value was, and that lowered our expectation of the future that came to pass, if it lowered our expectation about that compared to if we hadn't looked at the past at all, then we get a ratio here that's less than 1. We get a negative when we take the log. The past was misinformative about the future in that case. Whereas usually, if we look at the past and we've got a strongly repeating pattern, that will elevate our expectation of the next value that we actually get, and we get a strong positive information storage. So the strong positive value is what's happening in all the blue regions, and in the yellow we've got a misinformation that's happening. So when we encounter a glider, we weren't expecting to see that glider just by tracing the past background pattern, so we recorded a misinformation event at those ones. In contrast, we can look at the local transfer entities. So here we're looking at local transfer entropy to the right. So every pair of cells, we've got a source cell on the left and a target cell on the right, and then we're plotting the local transfer entities in a similar fashion. And what we're seeing this time is that the gliders that are moving to the right are very strong information flow events to the right. Whereas if we look at the transfer entropy to the left moving gliders are the strongest information transfer entities there. So again, that aligns with this perspective that the gliders are important spatiotemporal entities. They are misinformative from an information storage point of view. They are strong information flow events in the direction that they are heading. So they're the dominant information transfer entities there. And those results line up exactly with the conjecture about how computation could be considered in cellular automata. So they were really nice results at the time. You can reproduce all of those if you go to my JRDT toolkit. There are scripts there to reproduce all of those if you want to play with them.
Sorry to interrupt. Yeah, I'm noticing there is a negative mutual information here, and so I know that you explained why it is negative, but you see the expression of the local AIS, it is not actually a mutual information, because when we are like quantifying the mutual information, we need to do the expectation, right? Like the average information, so-called average information. So how could you? So my first question is it really a information? If yes, so how could we explain it in terms of information?
You're absolutely right. So it is specifically a pointwise mutual information. It's not an average mutual information. The average mutual information can never be negative. It cannot be negative. This has to be non-negative, 0 or positive only.
Mm-hmm.
Now, interestingly, in the history of information theory, so these days we talk of, when we say mutual information, we usually mean the average value, and we specifically use pointwise to talk about the pointwise values here. But interestingly, in the history of information theory, originally the term mutual information was used for the pointwise term, and the average term was very specifically referred to, very explicitly referred to as the average mutual information. So I think that's quite interesting, the way the nomenclature has flipped. But anyway, the local or pointwise values, yes, they can certainly be negative for the reason that I spoke about here in terms of the ratio of probabilities. Yep. And we can look at that. We can look at that in several different ways. So we can look at it in a very, I guess, traditional sense. When we talk about the mutual information, we'll often talk about it in terms of coding lengths. So Shannon entropy, for example, is often referred to as the average code length you would use to encode a certain variable. The mutual information between two variables, from a coding perspective, can be viewed as the code length you would save if you had to encode both of them and you took their joint information into account. It's the code length you would save by taking that into account.
Yes.
So similarly here, the pointwise mutual information says, okay, if I'm going to be encoding these two variables, and now I've got these two specific symbols for each of them that have come up, how much code length do I save for these specific symbols? Not on average, but for these specific symbols. How much code length do I save for these symbols by taking their joint distribution into account? Now, when I say how much code length did I save for these symbols, I might have actually incurred a coding cost for these symbols. So if I would save a coding length when they are two symbols that co-occur quite often, I will save code length on them. Thinking about English language text, for example, if I've written down a Q and then a U is the next letter, well, almost every time in English that I write down a Q, a U will be the next letter. So I can save a lot of coding by taking that joint distribution into account. So for specifically for the Q and U, I would save a lot of coding there. However, I might want to encode a rare pattern. So the Australian national air carrier, Qantas, is spelled Q-A-N-T-A-S. So there, if I write down a Q, but my next letter is an A, if I've used the most efficient coding pattern, then to encode an A as my next letter, that's actually going to incur a coding cost for me. So that specific situation where the Q and the A don't occur together very regularly, seeing a Q misinforms me that an A would come next, we can interpret that negative value of pointwise mutual information, we can interpret it as a code cost in this circumstance. It's how much extra code that I would have to use for the A in order for my overall average coding length to be minimal. Does that make sense?
I think it makes sense to me. Yeah.
Good. So the negatives, they're actually very important. They have a very strong meaning. They're counterintuitive at first, but they're very important.
Yeah. And I have another question, sorry. Perhaps Lizier, may you ask, is your question related to this?
I have a question, but you can go first.
Yeah.
You can.
My another question is about the information transfer. And you have used the transfer entropy here, but I think it's describing a binary relationship is from one source to a target. I mean, from one source variable to a target variable. So what happens if there are multiple sources? Like in your example here, you have y1 and y2 here, and I see here you are putting a priority on y1, and y2 is like a lower priority.
Yeah.
So so how do you to measure the transfer entropy that y1 and y2 give to x, or y1 and y2 they give to x in their own,
it's a good question. So you're right, there are multiple ways to handle that, and neither of them are more correct than the other. So I've got a why don't I open another slide? No, let's leave it. There are multiple ways to handle it in any case. Here, what we've written out is that we've said, let's have a look at the information flow from y1 to x first, then from y2 to x given y1. But we could easily have done that the other way. We could have said, what about the information flow from Y2 first, then from Y1 given Y2?
Yeah.
And they're both equally correct. Why should we choose one over the other? The answer is it depends. The answer is it depends. So you might phrase the question in a certain way. You might be more interested in the effect of one node on the target than the other, and so naturally you might look at the information flow from that one first. But in the end, it doesn't matter. What's important is that the joint information flow from them. So we could do a multivariate transfer entropy and ask how much Y1 and Y2 jointly provide for me about the target. And that's what we're effectively regressing in these two terms here. And it doesn't matter which way we regress them, which one we look at first and which one we look at second. They'll sum up to give the right answer, as they should. So the one term that doesn't change is that joint information flow from both of them together. You don't necessarily have to break them down then. That's the thing. You could just report the joint information from them together if you didn't want to prioritize one over the other. But there are good reasons, there are good reasons to be interested in the pairwise transfer entropy from one or both of them, or to be asking about the conditional information flow from one or both of them. It's kind of coming back to the idea of information decomposition. There are many different ways to decompose the information across this set. Neither way of doing it is more correct than any other way. What's important is that they all are consistent in the end, and whichever way you put them together, you properly get the right answer in the end. But the way that you choose to decompose it might be different depending on which question you want to ask.
Yeah. It reminds me the Farley's work, like to measure the synergistic, the redundant information and the unique information. And is it possible that it could be used in such a case here?
Yeah, absolutely. So you can go and so I haven't included information decomposition in the talk at all, just to because we could talk for hours on information decomposition. But yeah, of course we can. So we could go inside the transfer entropy and we could ask how much unique information am I getting from Y1 about the target that I did not get from
Y2.
I did not get from the history of X, or now I can contrast it with Y2, what I get uniquely from Y1 that I didn't get from Y2, what do I get synergistically from both of them, and so on. So yeah, we can certainly go and decompose all of these terms. We can absolutely do that. So again, thinking about it from an information decomposition point of view, this is one way to make a summary of that decomposition, I guess is a good way to put it. In information decomposition, there are so many terms that you don't necessarily want to be dealing with all those terms all the time. There's just too many. It can create too much confusion. You want to have a good summary. And I think these, not to take anything away from information decomposition, because I love that. It's one of my areas of research. But I think this is one very good way of summarizing that decomposition that aligns up with a lot of the questions that people tend to ask.
Yeah, I see. Maybe there's another question from Yuanbing Laoshi.
Okay. Okay. I have a question.
You can start first.
Yeah, I have a question about the experiments on C. I think it's a toy example to show how the local definitions work, right? And but for these pictures, I want to know how do you prove these definitions functions are consist or similar in a CAs with different rules. And I have the questions because it's that's for the picture because they are the distributions the pictures of the distributions are really different from the raw pictures that I just use my eyes to look at. So is there any ground truth to be used for comparing it with this distribution. Yeah.
For the cellular automata?
Yes, for some cellular automata.
That's a good question. The answer is no, because to some extent, the probability distributions that you're going to use to evaluate these they're always going to be subjective in some way. So what I've done here in generating these particular diagrams is I used what I wanted to capture was something as close to the transient dynamics in an infinitely sized cellular automata as I possibly could.
Oh.
If we've got any finite size CA, then that finite size CA is going to reach an attractor within a finite number of time steps because it's a deterministic dynamical system. So if it's of finite size, it will reach an attractor at some point within some finite number of time steps. Once it reaches the attractor, it's just going to undertake periodic dynamics. So on that attractor, if you have a long enough history, you will only measure information storage. You won't measure any information transfer. So to see interesting information dynamics, you really need to be looking at transients to an attractor. That's sort of point one. And so to look at interesting transients, I thought the best way to look at that is to try and mimic an infinitely sized CA to the fullest extent that we can. And so I used, I think, 10,000 cells, and I only ran them for 600 time steps. Now, that will give a reasonable approximation to what the transient dynamics would look like on an infinitely sized CA, but it's never going to be exactly that. You know, the next person along might decide, okay, well, I would have done it with 1,000 cells for only 100 time steps, and maybe the probability distribution function will be a little bit different because of initial conditions and so on. So that's why I say I don't think there's strictly a ground truth, and there's not really, as far as I'm aware, there's not really a way to analytically write down what those probability distribution functions would look like in that case.
Okay.
Does that make sense?
Yeah. Yes. Yeah.
Okay. Shall I keep going, or is there another question?
Yeah, you shall continue.
So that was our example with CAs. Moving forward to think about what we can do with this in neuroscience experiments. What I wanted to do was not so much go into huge detail about any specific experiments, but kind of stay at a high level and think about and tell you a bit about a classification of what we could do with this in neural data. So in short, what we can do with these measures now that are established is to answer specific meaningful questions about information flows in neural settings. So the classic experiment is to say how much information is flowing between region A and region B, for example. And then we could ask about how that changes under various conditions, or what the dynamics of it are in time if we were to use the local transfer entropy, for example. So that's kind of the classic question that we might ask about neural data. But then building on that, the key question is, what can such modeling tell us about neural information processing? And so I see sort of three classic experiments, three classic things that we could use it for. So the first thing would be to characterize different regimes of behavior. So using our measures of information storage and information transfer to characterize, for example, how patients with one certain neural condition might be different to controls, or how modulations to someone's brain, like different neurotransmitters, might change their information processing dynamics, would be the kinds of things that we would do under this first set of insights. The second kinds of things that it can tell us about neural information processing is how to understand the space-time dynamics of information flows. So this is now thinking about perhaps the local transfer entropy and how that can tell us about the dynamics during a cognitive task, the dynamics of information processing during a cognitive task. And the third key area that this modeling can tell us, where this modeling can tell us about neural information processing, is in terms of functional and effective network modeling. So taking time series, producing models, for example, information flow networks, model what's going on inside the system. And again, looking at what that tells us about the dynamics that are taking place. So these are sort of the three classes, I guess, of insights that we can generate with these tools. And what I'll do for the rest of the talk is just walk through a couple of examples for each of these at a very high level to paint the picture of the kinds of things that we can do. So it's the first one about characterizing different regimes of behavior. So here the aim is to characterize behaviors and responses, neural behaviors and responses in terms of information processing. For example, we might ask how information flows between two or more brain regions change with neural conditions. So we might ask how subjects with one particular brain disorder, how information flow between a pair of brain regions compares between that group of subjects and a group of controls. For example, like ASD, autism spectrum disorder subjects and controls. Or we might ask how the dynamics of information flow change with respect to different stimuli that we're providing the person. Or we might ask what happens as we're sweeping, for example, a neurotransmitter and making changing the brain through some critical phase transition. How is the information flows changing while we're doing that? This is the kind of thing that I mean. And so to look at the specific example here, this is an example where we looked at how subjects with ASD, how information storage in their brain changed compared to control subjects. So here we've made two separate MEG studies where we looked at contrasting active information storage across the brain in resting state activity between these subjects with autism spectrum disorder and controls. Now, two separate studies here. There was a smaller study where we looked at a smaller set of sources that were selected based on activity during a related task. And then the second study looked at 478 sources, so across the whole brain. And here in ASD, the macroscopic behavior is certainly more reactive. There's less use of priors observable in the way that people are behaving, and there's less impulse control. So there's certainly more bottom-up than top-down kind of behavior seems to be going on here. So we might have some hypotheses that there might be less information storage there because of those dynamics. We might hypothesize that. And indeed, that's what we saw, that there was lower information storage overall across the brain, and specifically in certain areas, including the hippocampus in the ASD subjects. So that was quite interesting. That the hypothesis about the macroscopic behavior having less use of priors, for example, and being more reactive, mapped quite directly to the lower level, the microscopic active information storage here. That was quite interesting. There's no real reason that they should map so well across levels like that, and yet they do. And so as I say, it's kind of fascinating that we've got the dynamics at both the macro and the micro level matching there, because this idea of the less use of priors in terms of the behavior matches exactly an interpretation that you can have for the active information storage on the brain, on the neural dynamics there as well. So the decrease in active information storage also, interestingly, correlated with the severity of symptoms for certain areas. And it was also interesting that there were no significant changes in power in the alpha band or the autocorrelation, functional or signal entropy, which were some simpler measures that one might use as first pass to try and look at, for example, the autocorrelation function you might use to try and study information storage, for example. But you certainly need this more complex measure in order to be able to see this distinction in what's going on. So that's sort of a classic example of that first type of study of characterizing different regimes of behavior by studying the information processing going on at that lower level inside the brain. The second type of study was about space-time characterization of information processing. So looking at, for example, how we can use the local measures of information storage and information flow to understand the dynamics of what's going on here. So there are different aims that we might have here. So we might want to look at highlighting information processing hotspots going on across the brain. And here, just as a side example, to show how general these measures are, I've included an example of collective fish behavior here, where we were looking at the movements of fish in a tank. So we've got these little tracks tracking out the movement of different fish and what the fish are doing. We had this small group of 5 fish conducting a U-turn. So I can't remember which one of these fish turned first, but one fish turning to cause the other to turn, which caused the next one to turn, and so on. And we can see that happening through time here. The angular heading of the fish are changing one by one as they're turning around. And so we're then coloring what's going on in those turns with transfer entropy. And what we were getting was that the leading fish, the ones that were turning first, were transferring more information to the later fish. So we had a lot of outgoing strong TE from the early turning fish, and then we would see misinformation from the later turning fish because their turns don't affect anyone else. There's no one else left to affect after them. So again, highlighting information processing hotspots is something that we can do when we're looking at these local values. Here, for example, seeing strong transfer entropy around the turns in the fish. We can, of course, use the information processing dynamics to help explain the real dynamics in the system. So here, what we were looking at was button presses. So we had a neural experiment where we were measuring what was going on in different areas in the brain, specifically here, motor control areas and motor execution areas. So we're measuring transfer entropy from motor control areas to left and right motor execution areas. So the person had a choice between pressing a left mouse button or pressing a right mouse button. So with their different hands, I should say. They could press it with their left hand or their right hand, and we're measuring the information flows from the motor control area to the 2 motor execution areas. And right about the time when the button was being pushed, we saw a large difference in information flows between, contrasted between flow to the right and flow to the left motor control areas, right when the button was being pushed. So we can use these dynamics of information processing to explain the dynamics of what's going on in that cognitive task. The third aim that we might have is to try and validate conjectures on neural information processing. So not just sort of unpacking what's going on, but if we already have a prior idea on what's going on in the brain, like with theories like predictive coding. So we have strong conjectures about what's going on. We can actually use these measures to come in and investigate those conjectures and actually check whether they hold water in terms of what they're saying about when and where the information flows should be. And that's the next example that I want to show here. This was an example where we looked specifically at predictive coding. So because predictive coding makes very strong conjectures regarding when and where information should be stored and transferred in layered neural structures. So here what we did is we looked at an MEG experiment where people were undertaking what we call a Mooney face house detection experiment. So Mooney simply means we've got these sort of moon-shadowed pictures. And what would happen is the experimenter would prime the person and say, I'm about to show you an image. Tell me if that next image is a face. So they're priming the person to check whether it's a face or not. And they might see a real image of a face or something that's garbled like this with similar statistics, but is not a face. Or it might be about a house. They might prime them. Please tell me whether the next image is a house. And again, show them black and white pictures. One might be a house, one might not be a house. And they have to answer whether it's a house or not. So here, predictive coding makes very specific conjectures about when and where information processing should take place. What it would suggest is that firstly, so overall, I should say, predictive coding suggests that the top-down information flows, the higher order areas, should prime the lower areas for prediction. So in suggesting, is the next image going to be a face, that should prime the lower level face recognition areas. So they should hold on to that information. They should somehow store the information that they have to be primed about what might be coming. And then when the information comes in from the visual system, predictive coding suggests that errors would be communicated up the hierarchy then after that. So based on predictive coding in this specific experiment, what we should see is that when we prime a subject to see a face, then the higher level face-specific area in the hierarchy we should see an information flow from that higher level area to the lower level area in order to prime the lower level area to see a face. Predictive coding suggests that transfer should specifically be proportional to alpha and beta strength in those regions. And then once that information reaches the lower region to prime it, then it needs to store that information. It needs to store that I'm now primed to see a face. So it's changing my state. My state is storing that information that I'm primed to see a face. And similarly, that information storage, predictive coding suggests, should be in the alpha and beta bands. And finally, we would expect that stronger storage of that priming should be proportional to performance on the task. So if I'm priming myself better, I should be better able to predict. Not to predict. I should be better able to detect whether I'm seeing a face or not a face in the next photo. And that performance is measured by reaction time on the task when I say, yes, it's a face, or no, it's not a face. And so we measured information flow between higher and lower face recognition regions here, and we measured the information storage in the lower level face regions. And we found that all of those specific conjectures from predictive coding, we found evidence for all of them, which is really nice. It was some of the first evidence for this particular theory. So it's a really nice use of these information dynamics, going down to this computational level and finding evidence for this particular theory. Now, what I should say is that it's not all rosy. Not all of the predictions that predictive coding makes we were able to find evidence for. So we didn't find evidence for house priming, for example. We didn't find evidence for the error signals. If someone saw not a face, we didn't see that error propagation going back up the hierarchy there, in fact. So it's not like we found evidence for everything that is suggested, but for some things. And perhaps there can be more searching or refinement of hypotheses. And again, these techniques are there now to try and address those hypotheses. So the last one that I was going to show briefly is thinking about effective network modeling. So this is the third area that I was talking about, that these measures very naturally fit in terms of trying to unroll what's happening in the brain. So they fit in really well here, because what we call the inverse problem is, if we've only got neural recordings, for example, we've only got time series and we don't actually know what the system is structured like, then we have this inverse problem. We want to infer a network model. And there are many different types of network models that we could infer. In neuroscience, for example, we often infer functional network models that just tell us about the relationships, statistical relationships between nodes. Effective connectivity analysis is about inferring a minimal circuit model that can explain the observed dynamics. And information transfer is much better placed here. Now, without going into all the details about the algorithms, coming back to our conversation a few minutes ago about Y1 and Y2, and why would we preference information from Y1 rather than Y2, for example, what this approach is trying to infer is not necessarily, is it Y1 or Y2, but it's trying to infer who's the set of parents for X. The order of that set of parents doesn't matter. The end goal of an effective connectivity analysis is to infer who the set of parents is. There are other things we can do. We can do a directed functional analysis where we're just looking at pairwise transfer, for example, but an effective connectivity analysis is about coming up with that set. So this is the job of a new toolkit that we put together called IDT Excel. We brought MyJIDT together with the Vibral Group's Trent tool, and we made a new tool called IDT Excel specifically for effective connectivity analysis from neural data. So thinking about this, this is a nice diagram in terms of thinking about it. This is a diagram from one of our papers performing a validation study. So what we did in this validation study is we started with a particular ground truth, and we used that ground truth to generate some different kinds of time series, both vector autoregressive and neural mass model generated time series. And the idea is that these are the kinds of time series that we might be taking and analyzing without reference to what the actual ground truth network is. And we would like an effective connectivity measure to somewhat replicate the underlying ground truth here, because we're looking for inferring a minimal circuit model that can explain the observed dynamics. Well, in simple cases where we've got all of our nodes are observed, there are no hidden nodes, there's no other funny business, we've got, you know, a general exploration of the dynamics. In those circumstances, we would expect an effective connectivity technique to come close to the ground truth. We wouldn't necessarily expect that in most neural experiments, because there are just way too many hidden nodes and confounds and so on. But in a validation experiment, we would expect that. So here what we've done is we've taken those starting time series and we've compared just a pairwise mutual information, which is like correlation is a functional connectivity measure. We've compared directed pairwise transfer entropy, which is a directed functional connectivity measure, and we've compared this multivariate transfer entropy, the real effective connectivity algorithm. Again, there's a lot behind how that algorithm works, but think of it as just inferring that set of parents in the end. And what we get is a good validation that for these kinds of simple network dynamics, where we can expect the outcome to be quite close to the ground truth, we do indeed see that. So functional networks sort of infer connections everywhere. The directed functional networks are a bit more like what we would like to see, but we can't really expect those given they're only a pairwise approach. We can't expect them to be too close. But the proper connectivity, the proper effective connectivity approach gives us something much closer to the real network, where I should say here, red is false positives, green is true positives, and yellows are false negatives. So we're getting quite close here, and it gets better the more data that we have. So this was a nice demonstration of efficacy of the technique at scale, in terms of efficacy, in terms of both time and accuracy of what we're seeing. You know, at that point, I might skip the last couple of slides. They're going into some of the finer details of how these techniques work and some of the later things we've been doing. But I might just push forward to the conclusion, which is to say what we've talked about tonight. We started off with the philosophy of what it means to be measuring information dynamics in the dynamics of complex systems. And so that's why we call this approach information dynamics. We're looking at the dynamics of information processing in these systems. And we're using this to model these operations on information on a local scale in space and time. And that means that we don't have to rely on qualitative descriptions. We don't have to rely on conjecture about what's happening in the computation. We've got the quantitative tools to do it. In particular, what's important is that work we've been integrating the theory, empirical enablers and applications here. So we've been developing the theory, we've been developing the empirical enablers like JODT, and in making the applications, that helps identify where we've still got shortcomings in what we are seeing. The last, again, I don't really want to talk through this whole slide, but the last slide was about some of our recent work was identifying that we were getting inflated false positives when we were dealing with fMRI data because of some of the digital filtering that was taking place. And sometimes with problems like that, it's important that you're working across both the theory and the applications. Otherwise, you don't see these problems. So once we saw this problem, we were able to go back and develop some more theory to eliminate problems that were being caused by digital filtering and to work out how to properly correct for autocorrelations in the time series to properly assess the statistical significance of any pairwise measure in these kinds of strongly autocorrelated time series. So the last thing we did was that we looked at what can these measures do for us in a neuroscience setting. We looked at this classification of 3 kinds of experiments looking at classifying or characterizing different regimes of behavior, space-time characterization of the dynamics of information processing, and effective network inference as another large and growing application area of these measures. So that's it from me. Thank you very much for the opportunity to chat. And I guess we'll take a few more questions.
Yeah, I do have a lot of questions, but let's welcome our audience to have their question first. So yeah, if you have question, you could unmute yourself and ask.
Okay, I can provide a question at first. Yeah, it's as for the brain structure, right? And for these structures is for now is comes from the biological knowledge, right? For the I see the structure figure is it's like some there are many notions which is related to some the period knowledge, and I'm curious about it is possible to discover this macro structures automatically from the data by the information theory. I hope I can express my question clearly.
Yeah, it's a good question. So, and the answer I think is kind of mixed. So in the validation study here, we certainly want our measures of effective connectivity to replicate what we're seeing in the underlying ground truth. Because here there are, as I say, there are specific conditions that this experiment's taking place under. There are no hidden nodes. The system is kind of allowed to explore the full range of dynamics that it's capable of, and so on. And under those conditions, you can expect the effective connectivity measure to replicate the underlying ground truth. Those conditions are they're just not met in real neural data. They're just not met. There's too many hidden nodes. The data is usually too short for the system to explore too many modes of dynamics, and so on. And you just there are typically a lot more connections there than you are capable of being able to see and differentiate the highly multivariate patterns that are going on. So I don't think they're going to be able to fully uncover real underlying neural structure. But I don't think that's a big problem. There are ways to do that anyway. So we can do that, for example, with DTI is one way. So track tracing with fMRI and other related techniques, we can do that already and pull out the structure. So we don't really need information theory to do that anyway. And the fact that one thing I didn't mention is that effective connectivity will be particularly sensitive to the kinds of data that you're feeding it. So if you're getting a person to do one cognitive task and then to do another one, the effective connectivity should actually look different between those. The structural connectivity won't. The structural connectivity will be exactly the same, but the effective connectivity will be different. And I think that's actually an advantage. We want measures like information theory to reflect the dynamics that are going on. We want to see different structure reflected from those different tasks. So I think that's actually a good thing that it wouldn't do that, if that makes sense.
Yeah, I think it's really related to some specific text. Yeah, and I just thinking about how can we apply the local definition from this multi-scale perspective, because for this measurements it just be calculated in the same level or scale, but if we but I can also calculate the transfer entropy from the different scales, from the macro level to the macro level, or I can compare the mutual informations from the different scales. So I want to know from your viewpoint, it is meaningful, or is what it can provide any insight? Yeah.
Yeah.
Okay.
Yeah, I absolutely think it's meaningful. I mean, if I come right back to some of the early slides that I had here on information theory for complex systems, one of my favorite sayings about information theory is that it's all about questions and answers. So, asking a question about how does the information in a neural variable at one level relate to a neural variable at another. For example, we might be talking about activity, overall activity in one brain region, and how that's predictive of spiking patterns, which is at a much lower level in one particular neuron in another region. And that's still a meaningful question. If we phrase that question properly, it's still a meaningful question to ask. It's fine that they're variables that are acting at different levels, but we can ask how much information we get from one about another. It's still a meaningful question as long as we phrase it properly and are aware of what we're asking. I don't see a problem with that. In terms of what I've been going through here, thinking about breaking down the information processing. Yeah, usually these variables are going to be variables at the same level in the system usually, but that's not necessarily the case. You can imagine having one of the variables here that's from a different level, and what the way we could interpret that. For example, let's say variable A, variable X, Y, and B are lower level variables, but variable A is a higher level variable. Maybe it's summarizing the activity in a different brain region. Maybe it's an average activity across that brain region. So by bringing it into the model here, we might use that variable as an input to the other ones that we're trying to explain. And that's fine. We're now making our model of X and Y and B, for example. We're making our model in terms of some of their sister variables at the same level, and also in terms of this macro variable from another region that's summarizing the activity over there. And as long as we're aware of that, we're aware that our model for X is about modeling the information processing in X in terms of its own values, in terms of the values of Y, and this macroscopic summary of what's going on in another brain area. That's perfectly fine. We've phrased what we're doing in a very sensible way. Does that make sense? I say it comes back to this idea of questions and answers, and properly understanding the question that we're asking and what we're doing by doing that.
And I just feel it's hard to interpret this just definitions, especially for the local definition. If I want to define some local information measurements through different multi-scales, so I have to find the corresponding meanings behind it, and I find it's very difficult.
It's always difficult when you start mixing them like that, but I don't think it's impossible, and I think it's an okay thing to do as long as you're trying to put a proper interpretation on it like that.
Okay, I see.
I should probably go in a few minutes, guys. I'm afraid we're finishing a bit later than I thought we might already, so I should probably go in a couple of minutes. I'll happily take questions on email later, but maybe just one more, and then I should probably go.
It's close to the end, so maybe we have no.
If can I ask a last question before?
Okay, last question. Okay.
Okay. Sure.
So with regard to the earlier discussion about the autism spectrum disorder with so for that particular experiment, and when you talking about the active information storage, what is the so what does this tell us in terms of these the hypothesis of how this dynamics works in this specific experiment or this study?
So here it was very much exploratory at this point. This was very much exploratory, just to have a look whether there was anything different, in fact, at all. So we're just looking at resting state activity and looking at the intrinsic dynamics of those different MEG beamform nodes across the brain, and looking at what differences that we saw in their information storage dynamics between the ASD subjects and the controls. And yeah, we certainly saw there was a lower average information storage overall, and specifically in some brain regions, strongly across the population. So here it's interesting that we can interpret the macroscopic dynamics of ASD. We can interpret macroscopically the behaviors that people exhibit in terms of seemingly being less predictable from their past, seemingly relying on those priors less. And those same interpretations apply exactly to what a lower active information storage would mean, that those micro brain dynamics are also less predictable from their pasts and seem to be acting with a lower prior on their pasts. Now, in terms of a hypothesis, I think it's difficult to connect the two. I'm not sure there is a great explanation for why you would see that exact same kind of dynamical explanation at both the micro and the macro level. Now, as I always say, I'm not a neuroscientist. Maybe a neuroscientist might have an explanation, but I don't know of one. This wasn't really necessarily going after finding that result. It was more exploratory than anything else. And so, perhaps I guess it would be interesting if that led to further investigations to find out why that was. But I don't think there's an exact hypothesis that this was going and answering, if that's what you're asking.
Thank you so much. Really appreciate it. Yep.
No problems. All right. So yeah, I'm sorry to say, but I should probably go and help put the kids to bed.
Yeah. Thank you for your time.
And as I say, I'm happy to take questions on email from anyone afterwards as well, by the way.
Sure. Yeah, we can collect our audience question and we could send it to you later by email.
No
and
problems.
perhaps you could answer it by email.
No problems.
Yeah. Mm-hmm.
Okay. Yeah. So yeah, we can quit and close so we already finished.
All right, shall I stop mine?
Professor Lizier.
Yeah.
Thank you.
Yeah.
Well, thank you very much
very
for
much.
having me. And good luck with the rest of the seminar series.
Yeah, thank you. So
Yeah.
then our event will end here officially. So you may leave if you have other arrangements.
Yeah.
Cool.
Yeah.
Thank you, guys. I'll hang up my end now then.
Okay.
Yeah. If you have any new papers, can let us know. Yeah.
Will do. Okay.
Yeah.
Have a good weekend.
Yeah, have a good weekend.
See you later.
Bye.
Bye.
对
结束了，
那老师走了，但是就如果大家观众的还有一些问题的话，也欢迎就是在群里面就是问啊，然后问了之后我们可以对吧，就是收集一下，然后我们再 email 给Lizier，或者大家也可以直接发他的 email 问也没关系，都可以。对，
如果大家现在有问题，是不是你们也可以就是先讨论一下？可以。
看看观众有没有现在想对做一些后续的讨论
问题。
嗯，
就是我不知道是不是我听漏了，他说有一个就他有没有提到 causal gradient 验证的问题？就是有一块他好像说他可以去识别那个 subsystem，然后之后和 ground truth 验证好像是对的，是有这块。
有一个你说最后那个实验是吧？
对。
最后那个
就是那个算不算是识别一个有效的 causal gradient？
他那个好像只是给了一些，他那个我感觉更像是一个就是因果发现的这么一个工作，就是他先搞了一个对吧，就是底层的这么一个就是因果的这么一个 correlation，然后生成了一些数据，然后他再去做这么一个东西，然后去看有没有跟那个本来的那个 ground truth 对应上。 但是好像不是很就是 coarse graining 的东西。
OK，
如果我没
我听那块儿的时候，我在想其他的，所以可能有点听漏了。但我刚才听了全程，我都在想尝试把它那个模型跟 Space 那个模型对应起来，然后我发现好像它可以想成是一个 Space 的就是像是随机版本，或者是 partial observation 的版本，就是它那里相当于是没有 control 的 Space，它把所有的 x 就当做 input，然后最后输出一个 output。
state
然后
space。
它就是状态空间方程，
OK， 哦，对，
然后
对是。
但是它这里头是没有 control 的，就是只有历史的状态。然后之所以它会去找过去的 k 个状态，是因为它是 partial observation，因为所有微分方程都是上一时刻决定下一时刻。然后它之所以要用到过去的 k 个时刻的话，是因为它是 observe 其中几个 state。那这个其实是有一个天然的，算是 causal grading 的方式，就是你怎么去 partial，就是你 partial 哪一部分state 能得
嗯，
到最好的那个信息，应该是 information gain，那就说明
但是他
这个是
他好像没
好的
提到
数理化方式。
这个东西。
对对，他当时在讲那个实验的时候，我在想这个，所以我不确定他，因为我最后听他说跟 ground truth 验证是一样的，然后他有一个
嗯，
分类，我在想是不是这个，可能不是。
应该不是，好像没有到那个程度。对，
啊。但这个其实是可以当做一个因果涌现的定义去提的。
英国涌现吗？还是说英国发现？
呃，或者叫粗理化的方式。
对，其实我挺想问，就是它这个东西听起来就跟因果发现就很像，就 causal discovery 或者 causal inference 这种。但是没来得及问它跟这两个之间的关系啥的。
对 causal 这块可能，我刚才也想了一下 causal 的问题，然后我构造了一个反例是，假如有一个 state 就是由另外一个 state 控制的，但是这个因为其他 state 控制它也是有规律的，这就会导致
嗯，
这个 state 它对自身也有很强的，就是从数据上来看是有很强的因果性，但实际上也没有，所以它这个也是个统计学方法，它不能揭示因果。
你说的是类似于 co-founder 的那种感觉吗？
对的，就是它没办法
对，
分这个。
他好像是说的是没有办法分辨 co-founder，我好像记得他是这么提了一
对，
句。
所以那就不能往因果那边用。
对，但是他就格兰杰因就可以往格兰杰
对，
因果那
刚才那个，
边靠了，但是没有办法从朱迪 board 那边去走。对。
我想问一个问题，就是说它这个东西的应用上的话，那和这个主要的应用的领域是什么呀？就是它这东西，刚才他提到了一些在 neuroscience 的一些 exploration 的东西，但是它在这个真正的就是实际的这种应用里边的话，它是怎么来应用的呢？
呃，
它这三
我的
套三套东西啊，它这个
我的理解，它就是一套建模，然后它在 neuroscience 的，对吧？就是脑科的这个场景，然后做了一些对应，但是我觉得他也没有说清楚，说这个在脑科里面能做什么应用，更像只是一种建模吧。或者它也可以，比如说它能够去刻画一些这个 information 的这个关系，比如说什么从哪一个 variable 到哪一个 variable 的这种 information 的 transfer 就这种关系，但是其实它也没有办法说清楚这个关系它具体是什么，它只能说明这关系的大小，大概是这种感觉。
我有一点理解，当然它也有一
嗯
些 PPT 提到了，就我感觉它的定位是定位在非线性的，并且没办法写出微分方程的情景下用于建模的。
嗯，对，我也觉得是的。
就相当于是填补这一部分的建模空缺。
但这个东西确实跟我还是觉得它跟因果发现这一部分还是重合挺多的。对，然后包括他用了什么转移商，也是因果发现就是里面经常会用到的这么一个指标。所以对。
但是他说 local 哈，就是他说，比如说这个 local 的这个。
嗯
和这个，比如说就是比如尤其它比如说它就是复杂系统的这种的话，那它的这个就是它这个机制来说的话，那它在这个从 local 机制和这个 global 机制的这种，就是或者说从一个微观的到宏观的这种，呃这种怎么说呢？这种 measurement 是吧？那它这个那这个东西的话，其实还是没法度量的呀，因为这个东西的话，实际上这两个不是在同一个 representation 的这个架构上面、建构上面。
对它的这种跨尺度的可能确实不是很能度量，它更多的是同一个尺度下，比如说刚才说的那个 local，比如说 AIS，我觉得这个确实是一个比较独特的这么一个点，但是确实像您说的，就是它没有办法去做一些跨尺度的这样的信息的度量，或也不是说不能做，但就是意义不明，就像明哲也说的，就是这个意义可能就很难去
对，
解释。
就是我怎么去界定它这东西，就是因为它，就是我很难去提出一个很清晰的一个 hypothesis，对吧？就是这个我是比较
我
对，
我们可能需要分一下那个 local，它那里提到有两层 local 的意思，就是有
对，
一个 local 是跟那个 average 相对的，就是信息的事
对对，
件的商
是的，
管它叫 local 商，然
对，
后平均的商就 average，所以这是一个 local。然后后
对
面明哲提的那个应该是就是宏微观
对，
的那个
是的，
local，对吧？
哦对对对，
然后他在回答明哲宏微观这个问题的时候，他给的答案是他觉得信息是一个问问题的方式，然后这个问问题的方式你是可以在你的问题里加入任何抽象的东西的。换句话说，就是你可以把，当然这是我的理解，后面是我的理解，就是你可以把很多变量打成一个包，然后或者你可以引入一个新变量，就把它定为宏观变量，然后去算一模一样的东西，这样它就可以解决宏微观的问题了。所以它在宏微观这个 local 这个问题上，它是不受限制的。然后，但是至于像事件的那个和 average 相对的那个 local，它的应用点是什么？可能我就是因为刚才探讨也没探讨到，所以我也没有特别想到它
而且
是用到哪儿。
这个东西我感觉也跟那个自由能源里面那个 surprise 也很像，
哎，对，
对，但是也没时间讨论了，我觉得就是有点可惜，没想到它就只有2个小时，
嗯，
对，
对，
他也没
刚才那位老
耍是吧？
师问的，呃，
嗯嗯嗯，
您您说。
您说，
你说没问题。
我想问一下，刚才就童老师问的是指的宏微观之间那个问题。
对，我是指宏微观的问题，因为实际上我一开始最上来的时候，他刚开始 lecture 的时候，我其实就问了一个问
嗯
题，因为就从 information 的角度来说的话，就是如果把它放到一个整体的 information 的，包括 information transfer、information 的这种processing 和
嗯
information storage 的这个角度来说的话，那我们在 predict future 的时候的话，我觉得就是我们的信息，它不仅仅来自于这些显性的。来自于系统的 state 信息，实际上来自于很多系统内部的规则性的或者说规律性的信息，比如就刚才说的，它那个rule 54是吧？就是它比如说它那
嗯
个用那个 Sailor Autonomous 里边那个 rule，比如说或者说 glider 啊，或者说这些 blinker 啊，那这些的话呢，实际上它本身隐含的信息实际上是包含在它这个 rule 自己里边了。就这个 rule 呢，它这个实际上就是它实际上 rule 的话，它 define 了一个 dynamic，这个 dynamic 很大程度上决定了什么样的信息可以用这种 rule 来表现出来，而且的话呢，它会表现出一些规则性或者规律性的信息。比如说我们人的话，我们在 process 一个 information 的时候的话，实际上我们用了大量的先验的知识，是吧？或者说用了这种我们以前的经验也好啊，或者说我们一些这种物理的规则也好啊，规律也好啊，所以说我们把这些东西和你的信息结合起来，去预测一个 future。所以的话呢，那我们并不是只是把一个传统的意义上来说，就是说你只是把这个当前的 information 用这种互信息的方式，或者说用一个这种probability of 这种 stochastic 的这种 process 来做预测，那就是实际上就是我们实际上这些东西实际上是已经在它的一个更基础的层次的话， 已经包含了一些隐含的信息了。那这个信息和它的这种信息的度量了也好的话呢，它不在同一个维度上的话，那但是呢，实际上它在真正应用的时候的话，实际上它对这个系统的最后的这种 state 的展现啊，或者说最后的话，我们 predict 到什么样的信息，实际上是非常的核心的和非常关键的。所以我就说，这两个不同层次上的信息怎么来把它放在同一个尺度上面，或者说放在同一个 system 里边来共同的去衡量啊，包括看它的互相这种交互方式啊什么之类的，这是我其实最大的一个困惑。
我可能有一个不成熟的答案，但我个人理解，就您那个问题的时候，我也在想这个事儿，就是我感觉确定性函数它应该是随机函数的一个特例。那同理，人的这些先验知识其实就是一个确定性函数，它是可以写成一个微分方程的。那这个微分方程一定也是个随机微分方程的特例。那他做的这些统计学的东西，其实就可以等价于一个随机微分方程。所以按理说，这先验知识这些东西其实就是当做一个特例，也一并处理了。
但
它
是是
它是一个
这样啊，但是那
描述，
你在
嗯，
处理的时候的话，你的这种是，就是我们先验的信息的话，你可以想象它是经过大量压缩的，对吧？就是说我们，如果你要是传统意义上来说，我是只是通过一个 distribution 来做forecast 和 prediction 的话，那我的这个实际上我这个需要的信息量是非常大的。但是如果我有了这个鲜艳的信息之后的话，我可以把它换成一个 formula 了，或者说换成一个 explicit 的一个heuristic。那这种情况下的话呢，那实际上我的这个需要的信息量的话，这不在同一个格局上了，对吧？就是说，比如说，如果我们想看一个就是比如说他说最后我这个 information 的话，一个 information variable 的话，我比如说我以这种一个 state 这个 future state 的这个 measurement 的话，这个 future state 的 measurement 里边的话，如果我们是 highly compressed 的这种，而且实际上我们实际上真正看到的信息的话，也是在 highly compressed 之后的话再 represent 出来的。那这种情况下的话呢，就是我们用不着去用微分方程去做每一个 dynamic 的这种 forecast，而是实际上是我是把这个一些 compress 之后的一些 variable 的话呢，再去再把它重新给它就是做一些比较就是说显性的一些这个分析什么之类就可以了，对不对？那这个实际上就是在它这个系统里边的话，那就是和互信息的这个就是你这算出来的互信息和算出来的这个 future state 的这个需要的东西的话，那就差很多呀。
嗯，我想，对，这里又是两个维度的事儿，就是他用的所有建模方法都是用测度，所以就信息测度，然后信息测度的精度是没有微分方程那种高的，就是跟微分方程是多对一的关系，所以都是在
对
描述性质，但是并没有揭示本质。然后它描述
对，
性质，我刚才说等价于随机微分方程不太准确，但它是用于描述随机微分方程，所以它也能描述微分方程。就比如说，它最后互信息等于信息差，那就是一个随机的，不是，那就是一个确定性的微分
啊，
方程。
我明白。那这我同意，这我同意。
呃，
这个是，就是从那性质上来说的话，这我是同意。但是我就说
对，
是在实际
所以它也可以
应用
去
或者说解决上来说的话，我觉得就差异蛮大的，是这样。对。
嗯，我觉得是一个，我觉得它怎么说，可能需要把它放到现有的所有建模方法里头，然后去看它填了哪一块儿的空白。因为我能想到的，如果是线性系统的话，或者说能写出微分方程的系统的话，肯定有更好的方式。我们都不需要测度这种模糊的概念，就直接写出函数了，那问题就都很好解释。所以我觉得它可能定位就是定位在非线性的，然后又没有显示解的那些系统上，它能给一个模糊的定性描述。就定量的定性描述那种感觉，就可能这个是它填补的空白。
对，是哦。那但是就是说从这个角度来说的话，就是如果从自由能的这个角度来说的话，那它这套机制的话，就它的这套机制的话，那应该用自由能的这种方式的话，实际上也是可以把它就是可以把它就是统一化的，是不是？
就我对自由能那边了解不是特别多，但我有感觉自由能可能比它更抽象一级，
因为自由
抽象
能
几级。
也是从 information 的角度来说，是吧？从 information 的 optimization 上来考虑这个问题的，对吧？就是说，那他也是想从说一个最基本的这些 information processing，就是像因为他一开始上来就是比如像图灵的这个图灵机啊什么之类的话呢，就是实际上还是从一个最 fundamental 的 information 的角度来解释所有的这些过程的呀。所以我就是我还是还是有点困惑的，就是说它这个东西怎么能够，嗯，就放到我们的真正研究框架里边去，就像你刚才说的，怎么去填补它这空白哈，嗯。
对，我突然可能再加一个限定，就刚才说的是非线性的，不能显示写的，而且是要要时间序列的。
那所有的
自由能那
Markov
边，
就 Markov 这个或者 hidden Markov 的话，实际上那其实都有类似的规律，是不是？
因为我突然发现，就如果不考虑时间序列的话，也会有其他方法比它要好。对，它可能明确的就是要时序问题，然后带刚才那样的限制。
我发现听完之后，比来之前的话多了很多。
是的，是的。不过挺值得启发的，就是我可能还有一个问题，但是我可能也需要大家帮忙想一下，就是我一开始想的是，假如我们默认所有系统都存在一个完美的微分方程，然后我们现在只能部分的观测到它的 state，比如说它有100个 state，然后可以写出一个完美的微分方程，我们现在只能观测其中10个，所以这个时候它应该就是适用于这套模型的。然后他会发现这套模型可以通过，就如果只预测这10个的上一时刻，对这10个在当前时刻的预测量是不如预测这10个 state 比如说前5个时刻的预测量。然后，然后我想尝试把这两个模型都换成随机的状态空间方程的话，会有2种写法，就一种是直接就是上一时刻的 state 的一个函数加一个随机项，或者我可以写成上5个时刻的一个函数再加一个随机项。然后我是显然后者是更好的，但是我又没想明白这两个中间究竟差的是什么，就是把那4个 state 变成后面的就是拿到后面的随机项里头，究竟损失的是什么？还是说这两个是等价的？就是我觉得这个是它比随机的状态空间方程要好的地方，就是它把就假如它是成立的话，它能把随机的那一项写成显示的更早的 state 的方程。
你为什么会说他们是等价的呢？就是我觉得他们都
就
不是等价的。
我感觉我这个不能证，但是我感觉应该是等价，就是至少在用上是等价的，因为你都是从数据上收上来的东西嘛，你是可以把比如说前一刻的显示
嗯，
函数我们保留，前2到前5的我们就直接算一个它的随机项，然后我们直接扔到后面的随机项里，因为前4个状态也是个 variable，我们是可以写出它的那个。
有没有可能就是你把那个给扔到后面了之后，你又没有办法把它给拆出来了？
对对，这是个单向的过程。所以我觉得
对啊，
它可能相比于
你没
对随机的状态可方程这块，它是它的优势。
对你又没有办法把它给拆出来的话，那这部分的信息可能就损失掉了，因为对吧？你就把它给看成一个随机项，你跟其他的这随机项的信息就混在一起了。
我可能需要去找找，就是控制领域的有没有做类似的事情的人。我感觉应该是有的，就是把多个时刻之前的也写到。对，这个我可能得再看看文章。嗯，
嗯，那今天奥博应该想讨论的大概讨论完了是吧？
我没什么问题。
其他的老师同学还有什么问题吗？或还有其他想讨论的东西吗？或如果对，就是如果有针对这个 talk 有什么问题的话，也对，可以在群里面再继续讨论，或者就是给 直接给他写邮件问他也是可以的。那对，所以我们今天的活动就到这里了。对，
好，
那感谢大家的参与，也感谢奥博还有童老师，就是一起参与了讨论。对，那我们今天的就到这里了。